Hi everyone, my name is Benjamin Depardon and I work at UCIT, and today I will be talking about a tool that we develop which is called Analyze-It, and give you an overview of what it can do through the prism of specific issues that we encounter in HPC clusters that we call congestion and contention. First of all, who are we? Who is UCIT? So we are a French company founded in March 2015. We are headquartered in the south of France, in Montpellier, and we see and we envision that simulation, HPC, is everywhere. And every scientist, every researcher now has the need or will have the need to use at some point simulation, data analysis, HPC in its whole to solve their problems. And to do so, they will need to have access to resources that fully match their needs, that match their constraints, and they will do it through services. HPC will evolve to be consumed as services, and whoever is prepared for that, be it on the consumer side or on the provider side, will tremendously benefit from HPC in this way. And so at UCIT, what we do, we are an HPC company, and we develop tools, solutions, and processes to help our customers evolve to this next generation HPC, let's say. And we look at different aspects of HPC. Of course, the performance, so the time it takes to solve a problem. The cost, because infrastructures do cost something, whether they are owned and on-premise, or either rented to an external provider or through the cloud. And also something which is becoming more and more important is, of course, the energy side. It's not worth simulating stuff very quickly and at a low cost if you are polluting the earth. So you want to have a trade-off between all these three aspects of HPC, and that's what we are doing. And for that, we use data science approaches, and we apply that to HPC data. And we do that through tools, as I said, that we develop that embed these aspects and these mechanisms to explore and understand what is happening on HPC platforms, detect potential problems, and then recommend, find solutions to optimize HPC, both for the administrators, but also for the users, so that everyone can get the best of HPC with their combination of energy, time, and cost fitting their need and constraints. In this talk, I will be focusing mainly on a specific problem that can be encountered in HPC clusters, and I will define them right after, congestion and contention. And we'll be looking at the time, so the performance of the jobs, but also the cost briefly of the solutions that can be set up. Okay, so now let's dive into the subject. So first of all, what do we call congestion and contention on a cluster? Congestion and contention are two states that we have defined with customers that observe that their clusters were behaving sometimes not at full capacity, but still having lots of jobs piling up in queue. So these two states of the cluster have something in common, is that whether it is the cluster highly delivering CPU hours, so behaving correctly and delivering almost its full capacity or not, jobs can start to pile up in queue, and so the computing surface that is requested by all the users, the number of CPU hours that are in queue, start to increase, and the effect is that, of course, people get their result later, so they are delayed, which can be a problem if you have a deadline, whether it is for research and you have a conference where you want to deliver some results, or if it is for an industrial project where you need to have the result before the end of the month. This can be a problem. So congestion, what we define as congestion, is you have lots of jobs that are piling up in queue and waiting, and the cluster is not delivering its full capacity, meaning that you still have resources that could be used for those jobs in queue, but for whatever reason, the cluster do not allocate these jobs to free resources. Contention is the reverse, meaning that you still have jobs piling up in queue, but here your cluster is delivering almost its full capacity. So all the cores, the nodes are allocated to your jobs, but you don't have enough resources, or the resources requested do not fit into your cluster at the given moment, and you are not able to deliver quickly computing resources to your users. So some questions arise on what is happening. So you need to understand what's happening in the cluster. Is it a problem with the way the people are submitting their jobs? Do I lack resources to be able to sustain the requests? Are there some problems on the configurations of my cluster itself, etc., etc.? So how do we identify congestion and contention? So basically, we just have a look at the two metrics that we just defined. So one, on the horizontal axis, we look at the running CPU hours. So what has been allocated to the jobs, and that cannot be used by other jobs, obviously. Vertically, we have the waiting CPU hours. So what is piling up in queue? So what the jobs have requested in terms of CPU hours. We then define two targets. One is the target minimum cluster load. So basically, usually you want your cluster to be efficient and deliver and is used at the almost at its maximum capacity if it is possible. So here you will define, for example, an 80% ratio, saying that you want to be over this 80% cluster load allocated resources on your cluster at any given time. The other target that you set up is the maximum waiting load. So here it's more on a user side. It's you want to have some jobs in queue because and some computing requests, the surface of computing CPU hours in queue, because if you don't, then you will not be able, of course, to deliver the full capacity of your cluster in terms of running CPU hours. But you don't want it to be too high, because otherwise it means that your jobs in queue will wait longer and longer before being even scheduled and allocated resources. So, for example, you might want to define this target to twice what your cluster is capable of delivering in terms of CPU hours. This defines 4 zones. So the first one the one that you want to be in, is what we call the optimal state. You are higher than the target minimum cluster load and still below the target maximum waiting load. So basically here, your cluster is delivering almost at its full capacity, but still people are not waiting too much in queue. Here, the second zone is what we call the acceptable state, meaning that it is, as you see, a grayish yellow zone, meaning that here there is not many requests in terms of CPU hours. So not many jobs or not big jobs, whatever. But and your cluster, of course, cannot deliver its full capacity because there is not enough jobs to fill it. So it's acceptable. It's not what you would like to have, because it means that potentially, if you are always in this state, that your cluster has been over provisioned compared to what you need. But it can be also, for example, during the weekends or trough periods. On top of that, you have two other zones which define congestion and contention. So contention is on the top right. You use correctly your cluster, you are over the target minimum cluster load, and you are, of course, above the maximum waiting load that you defined. And congestion is the other one on the left. So let's have a look at real congestion and contention situations. So first one, a congestion situation. So this is an example of a cluster seen through its evolution of its states through 4 years, so from 2015 to 2018. 2015 was its delivery, its installation. So what we see here is that we are, for most of the time, into an acceptable state. This is the start of the cluster. People are starting to go into it, start to run their jobs, and the cluster starts to deliver its computing power. And as you go through the years, you can see that the ratio between acceptable and congestion state start to shift the other way, to end up in 2018 to almost 2/3 of the time the cluster is used is in a congestion situation. And this is quite typical to what happens on most clusters. Of course, you have a ramp up in terms of requests from your users. You have more and more requests, more jobs that come to the cluster, and at one point you cannot deliver everything. But here, the interesting point is that even though the cluster has many resources, it's almost never into the optimal or contention state, meaning that it's never capable of delivering its full capacity, which is an issue because either the cluster is over-provisioned or the jobs are not properly submitted, requesting too much resources, for example, which impacts the quality of service that the cluster is capable of delivering. Another example here, another cluster where we have something which is a bit more balanced between the 4 zones, but here we face contention situations. And we face it, as we can see on the right, we face these contention situations during 2 main periods of the year. So during summer, so July and August, there is a first peak of contention, and also in September, there is a second peak in this case. And this is a typical use case where the cluster, even if it is properly used, might need at some point, if there is some kind of urgency, to offload some of its job, some of its load to external resources. This is also, as I said, typical. We have something which is a bit more balanced, and we also have some congestion situations at some point. So we have multiple peaks as well, which need to be further investigated, because in this case, it's not happening all the time. There are some peaks. So either there could have been some new users coming to the cluster which didn't know how to submit jobs properly, or there has been some maintenance periods, or other stuff that So these periods need to be investigated. So how did we dig into these situations, and how do we explore them to understand what is happening? So this is where Analyze-It comes into play. So this is a framework that we have developed, which is here to understand what happened in the cluster and to be able to dig into the behavior of the jobs, the users, and detect potential problems first, and then find some solution to either go back to the users to recommend them to change their behavior, or to change the way the cluster is managed, it's administrated, to optimize its performances. So the tool in itself feeds on logs of the job schedulers first. So we support all major job schedulers: Slurm, LSF, SG, Toki, PBS. And we grab the information from them, and we provide through that hundreds of KPIs that allow to understand deeply what is happening. If those logs are not enough, we can also ingest other sources of data through what we call data enhancers, which allow to add some information which are more specific to some applications, for example, or some particularities of the platform, ingest that, and then explore that through Analyze-It. So let me just give you a quick demo of that through the congestion and contention plugin of Analyze-It. So this is an example of an analysis provided by Analyze-It for this congestion contention situation. The way it works, as I said, is that you need to define these 4 zones, and you do that through defining what we call the run ratio, so the maximum cluster load, the minimum cluster load that you want to have, and also the weight ratio. So let's say, for example, that I want to have 70% of my cluster at minimum that is used by the jobs, and that I allow 1.5 ratio of 1.5 between the waiting and the running capabilities. I can then see and define my 4 zones and see that in this case I am in an optimal state almost 40% of the time, acceptable state 30% of the time, and then I have 2 zones of congestion and contention, with quite a lot of contention actually. And if I want to understand a bit more what is happening, I can have also an overview of day by day, so a timeline of what happened on my cluster. So something I didn't say so far is that each dot that you see here is 1 day of computation of your cluster, so 1 day in the life of your cluster. And here you have a 1-year analysis of a cluster. So if I want to understand what happened here, for example, on the 22nd of July, just can click on it. I will find out where it is here in this graph. I was into this peak that I showed you earlier, and I can then zoom and see exactly what happened on the period. So I have 2 sub-periods where this happened. And for each day, I can then have the detail of how many CPU hours have been delivered and how many CPU hours have been requested and waiting in queue also. I can also zoom into the period to have an understanding on what types of jobs I had, how they were behaving, were they waiting for a long time before this day, or was they just submitted this day and executed later on, etc., etc. So this is the start to understand what happened on my cluster, on these congestion and contention situations, and then I can also use all the other plugins of Analyze-It to deep dive into what happened on the cluster and have a look on, for example, to have information about how much resources have been consumed by the jobs, who has been doing what, and who were the most the bigger consumers on my platform, and then dig again into that to have more details on the types of jobs that have been submitted by my users. So let's go back to these congestion contention situations. How do I solve that? So there are multiple ways, and these are just examples that I will be giving here. So one can be to update the job scheduler configuration if there is any issue with the partitions, the scheduling policies, etc., which might impact how fast the jobs can go into running state. If this is not the case, you might need to share the resources to attain a better allocation of your resources. For contention situation, this might be a problem of resources, so you might need to add new resources, so either update your cluster or change completely your cluster. Or you might also use external cloud resources to solve only transient peaks of demands. And for congestion mainly, you might also want to try to optimize the way jobs are submitted, because users tend usually to request more resources than what they really need in terms, for example, of execution time, number of cores, memory. So this might also be a way to reduce the time they spend in queue and increase, of course, the resources usage. So let's first focus on this part, the optimization of job submission parameters. Why would we want to do that, to optimize that? So if we just have a look at two of the parameters, two simple parameters. So one is the wall time, so the maximum execution time that the job is allowed to run in the cluster. So if you request a wall time which is much bigger than the actual execution time of your job, then it will increase virtually the waiting CPU hours compared to what you will actually need. But also your job will wait longer in queue because it is harder for the job scheduler to find a slot to schedule your job. The requested memory is a bit the same. It will be harder to find a place to schedule it if you request too much memory compared to what you have consumed. But it has also another impact, is that if you request a large amount of memory, you might be allocated a full node just to get the right amount of memory that you have requested. But if you are using only a few number of cores on this node, then it means that potentially half or 90% of the node is left unused because you do not use all the cores at first, and you won't need actually all the memory that you have initially requested. So this might create holes in scheduling. This might prevent jobs from executing properly quickly on the cluster. So what we try to do, and we developed a tool for that, is to predict the behavior of HPC jobs prior to their submission, so that we know in advance how much memory they will actually need when they run, and for how long they will run. So we designed a tool which is called PredictIt, which is a machine learning tool that feeds on cluster logs that train multiple machine learning algorithms to try to predict different characteristics of the job. So first, its state, trying to detect if there will be a failure in your job potentially, its execution time, its memory, and some information which are more meant for feedback to the users, such as an estimation of the waiting time and the time to results, basically the waiting time plus its execution time, so that the user can project itself before even submitting the job as to when the results will be obtained, to see if it fits, for example, with the deadline of its project. And so the idea behind Predictit is that this is a server that runs all the time, that queries the job scheduler on a periodic basis to get the latest information about the jobs that have been executed in the cluster, and periodically retrain its algorithms to improve, of course, its accuracy and to give more and more accurate results. The tool can be then used when it has trained either on the command line, if you want just to query it and ask, okay, will this type of job, how will it execute? Or it can be easily integrated with third-party tools through its REST APIs. So for example, we have integrated that through behind web portals to give some feedbacks to the users and to take automatic decisions as concerning the submission parameters. It could be also integrated directly within Slump, for example, as a plugin, submission plugin, etc., etc. So the idea here is to have a tool that will act on the submission workflow to try to optimize it and to provide as many information as possible, as accurate as possible to the job scheduler, so that it is able to do its job properly and with as much efficiency as possible. How do we work with this tool? So this is a multi-step process. So basically, the first step that we do is what we did earlier, just before, is that we first go through, analyze it to detect if there is any potential issue, any drift compared from between what the users request and what they actually use on the cluster. Then we see if this can be improved through parameter submissions. So this is one potential solution, as we said. And for that, then we use Predictit to train on what we call a generic predictor on the whole cluster. So we have a look at all the jobs running on the cluster first and see how well Predictit performs when it tries to do some predictions. We then assess whether or not it is good. And if it is good for production, meaning that if the accuracy and the repeatability of the predictions is good enough, then we deploy it in production. As I said, there are multiple ways of doing that. Plus, we also deploy just what we call the tracking script, which is a tool that continuously monitors the performances Predictit and test it on all the jobs that go through the system. Because potentially you might not want to use its prediction of Predictit on all the jobs that go through the system, but only a subset, because they are the most meaningful ones. And this is where we go back to analyze it potentially, to identify what we call workloads. So basically, a subset of jobs, typology of jobs that are meaningful to solve the problem. And they can be meaningful for multiple reasons. So for example, they can be because this is a group of users who are using a very demanding application that needs to be, that has a high impact on the system. This could be because you have identified a group of users who are trainees, for example, who don't know well how to submit the jobs, and you want to guide them through the submission. So we filter basically the type of jobs we want to use for training the algorithms. Plus, if we have other information, we also add external logs, external information to also guide Predictit and help it have more accurate predictors for these specific workloads. And we loop on that until we have something which is good enough to be used by the system. So let's have an example of a real application, but this is a toy example because it's been identified on a cluster running different types of jobs, but for a specific category of jobs where we only had 5K NAMD jobs. So NAMD is a parallel molecular dynamics software which is widely used by chemists. And on this cluster, we wanted to see if we were able to attain good predictions for this specific application on two targets, so execution time and consumed memory. So we did, as following the process that we saw earlier, we did it multiple times, and we first start to train only on the job scheduler logs, so on SGE logs here in this case. And what we try to do here is to have the perfect match between the observed execution time of the jobs versus what has been predicted. So we would like to have on this heat map a perfect diagonal of red squares, meaning that in this case we would be 100% accurate, which is not the case here. When we look at this, the results of the first iteration, is that we are only able to predict only about 30% of the jobs correctly, which is not very good, of course. We would like to be as close as possible to 100%. So we did a first round to add some information about the NAMD jobs themselves, and we gathered some information about the size of the problem, how many steps the job runs, etc., which are all part of the standard NAMD logs that we retrieved. So this is, and these are only input parameters of the job. So some information that are very easy to grab when you submit a job, because obviously the user who submits an NAMD job knows about all this. And we injected that through data enhancers into Predictit, and we improved the predictions by almost 20% on top of what we were able to do previously. So this is still not perfect, as you can see here, because we only are able to predict about half of the execution time of the jobs. So this is the first step that will need to be refined, but it gives a clear path of improvements for this tool and to better predict what will be happening on the cluster. The same type of result has been made and obtained for the memory prediction, where here we had even worse predictions at the beginning and even better performances when we gathered some information, some additional information about the NAMD execution itself, its input parameters. And 70%, more than 70% of the jobs here in this case are properly predicted. So this starts to be something which is interesting, because with this level of accuracy, you can start to think about integrating these predictions into the system and then use the results when you submit your job to better optimize your execution. So what are the outcomes of this? Is that this type of tool can really improve, because that then the result in production, it can really improve the job submission parameters compared to what they will need when they actually run. But to do so, having only the generic approach where you look at everything and try to predict that is usually not enough. You need to have other information that need to be aggregated, some metadata about your jobs that the job scheduler itself cannot grab. And some very simple and some very small amount of metadata can greatly improve that. Here, for the results that I showed you, we didn't even use all the input parameters that NAMD has. We only selected a subset, which is about less than 10 of them, which are the most relevant for its execution. And only with this small metadata on top of what the job scheduler provides, which are also important data about the job, we are able to really improve the performances of these predictions. Okay, so now let's go back to solving congestion contention and have a look at the contention part. I won't go into much details here, but let's have a quick look on how to solve contention through the use of external cloud resources. So I won't be talking here about how to deploy such HPC resources in the cloud, but more on how do you assess whether or not it is a good solution for you, and through the prism of how much will it cost to move that, because it is technically moving to the cloud might work for your workloads. You might even find better performances depending on the type of instance that you use, etc. But is it feasible in terms of budget? Because we know that HPC can cost a lot. So if running some specific workloads on the cloud costs much higher than what you have, it can be good if it is for a specific project and you have the money for that because there is a tight schedule. But if not, you want to know that in advance. You want to budget it. And so for that, we also have integrated with Analyze It, a plugin that we call CloudShaper, which also feeds on the log of your clusters, and which, based on what happened on your cluster, and you can select only a subset of it, a workload. So you select only, again, the relevant part, the peak that you had during this contention period, the jobs that were for this peak, you select this workload. And then through CloudShaper, we analyze how much it would have cost you to run these workloads on the cloud. And we do that by using different strategies, different placement strategies, the selection of different types of instances with different performances. And we try to product that in a way that is meaningful for you and which is similar to what you understand when you are talking about a non-prem HPC cluster. So we have a look of the costs through, as you can see here, five categories. So the main one, of course, the two main ones are, of course, the computation part, so the compute nodes, and the storage, if you need or not a high performance file system, but also all the external and needs that you have around that to make the HPC work. So the services that you need, the visualization part if you need to, so to have specific resources for that and tools, but also the data transfer, which have some cost in the cloud, in AWS, which is the first target that we have here in CloudShaper, but we are adding soon also the comparison with a model of your on-prem clusters and also other cloud providers. So to conclude, the process that I showed you today and the tools that I showed you today are here to help better understand what happened on your cluster and dig into, here in this case, specific situations that are congestion and contention to detect potential needs of improvements and to detect also what caused these situations, these issues on your cluster, and some ways to solve that, or at least improve the productivity of your cluster and the quality of service that you deliver. The key part behind all this is that to do so, you need some information about what you do. So you need to gather logs, metadata about your cluster, about your jobs, and store that so that you will be able to post-process that, analyze that, and we provide some tools to do that. There are other tools as well, but here we have tightly integrated tools that allow you to have a look at your logs through different prisms, through different strategies, which allow you to quickly identify what are the problems, where they come from, assess some opportunities to improve everything, and of course, in the end, increase the productivity of your clusters, of your HPC resources. Thank you very much for your time and attention. And if you have any question, feel free to ask them or to send me an email, of course. Thanks.